The function features we're going to talk about today are key. Let's jump into this immediately. Here we go. Let's start the ignition. And I mean that in terms of we're going to begin doing math. Okay, and let me just kind of drag my, be over here. I think I do. Drag my picture over there. There we go. For each of the following functions, find the following. Function doesn't meet one of these criteria, for example, just write NA. That's just fine. Perfect. Yeah, let's get working. So we're going to go over, here's my function, and why don't I just resize myself? I'm going to make myself a little bit smaller. There we go. Perfect. Fit right down there in the corner. Look at that. Let's first start with domain and range. We're going to go through 3 of these, and we kind of skipped some of these in class. That is okay. We're going through them now. We're going to start with domain and range. All right, so let's do the domain and range for this function here. Here we go. The domain. Domain, that's the lowest possible x value. So remember, if I were to look at all these points and I were to write all the points down, what would be the the lowest possible x value? Well, this arrow keeps going. It goes forever down. It goes forever to the left, just going down faster than it's going to the left. So the lowest possible x value, since it's going forever, will be infinity. The highest negative infinity. The highest possible x value will be infinity. Now let's do the range. The range, the lowest possible x value for the range, lowest possible y value for the range. It appears it goes down forever, so there is no lowest possible value. It's headed off towards negative infinity, and the highest possible value for the range, it looks like it does reach 4, so it goes up to 4, and since it turns around at that point, we can assume that it hits that point, which means we can use a bracket. Let's keep going. B, x and y intercepts. The x-intercepts are where it crosses the x-axis. Let's go ahead and find those points. Crosses right here, and it crosses right here, and let's write those down. The x-intercepts are 1, 0, and negative 3, 0. The y-intercepts. Y-intercepts. Where does it cross the y-axis? Right here, which is the point 0, 3. This is fun. I'm having fun. Nice. 0, 3. Fantastico. Switching colors. Green. All right. Intervals where the function is increasing. So we'll do increasing, decreasing, and constant. Always talk about all of them. And where is it increasing? Increasing is if we're biking from left to right, where are we biking uphill? We're biking uphill here all the way until we get to 1. Those are the x values. Remember, I'm only interested in the x values where we're biking uphill. It's increasing from negative infinity up to negative 1. And we can just use parentheses there. Yep, for increasing and decreasing, remember we just use parentheses where the spots where it's changing from increasing to decreasing, or at the endpoints. Okay, where is it decreasing? We're heading downhill from negative 1 this direction. Okay, so that goes on forever. That's from negative 1 to infinity. And where is this constant? Constant, remember, looks like a horizontal line. It's constant nowhere, so we just say not applicable. And lastly, intervals where it is positive and negative. Positive and negative. Positive, where are we above the x-axis? Where are we above the x-axis? We're not above the x-axis at these points, so those will not be included at the x-intercepts, but we are everywhere in between. We're above the x-axis from negative 3 to 1. Fantastic. Where are we negative? Where are the x values where we're below the x-axis? We're below the x-axis for all these x values and all of these x values. The graph is below. Okay. So it's negative from negative infinity up to -3, union from 1 to infinity. Okay, I've kind of explained, gone into a little bit of detail with these. So on these next examples, I'm going to kind of race through them, or not race through them, but maybe go a little bit faster. The domain. Domain, every possible x value, all of them are possible. There is no spot where we can't write an x value. The domain is from negative infinity to positive infinity. The range. The range, what is the lowest possible y value? If you're heading down this way, if you're to tilt your head sideways and look or turn your paper, the lowest possible y value is 0, and 0 is included. You can have a point that is 0. Probably this x-intercept right here. We'll talk about that in just a sec. So from 0 up to infinity. Okay. In blue, let's do part B. Oh, I changed the colors up. Please forgive me. Please forgive me. X-intercepts, there's only one. That's the point. -1, 0. Cool. Y-intercepts? Or does it cross the y-axis or the line x equals 0? The point, 0, purple. Making all sorts of marks up on here. Okay. Part C, intervals where the function's increasing, decreasing, constant. Or are we biking uphill? If we're biking from left to right, the direction we read a book, where are we biking? Uphill. We're biking uphill from -1 all the way. From -1 all the way to infinity. And we use parentheses there, even though there's a dot, or even though we included that in our range, right? That point. Okay, and then where's it decreasing? Decreasing from negative infinity up to -1. Awesome. Constant flat, not applicable. Class. For D, positive, negative. Positive, negative. Where is it above the x-axis? Interesting. Not on the x-axis. Where is it above the x-axis? So there are actually two intervals here. It's above the x-axis from negative and infinity, right here. But it crosses, and it crosses at that point. So it's above the x-axis from negative infinity to 1, but not at, at -1, but not at -1. So we actually have to talk about this two separate intervals. Two separate intervals with a point that's missing between them. That's kind of awesome. Negative. Not applicable. Now the fun. Domain. Let's do this thing. Okay. Domain is the lowest possible x value, which is included, is -4. How far to the left can we go? Or if we were to squish them on the x, -4, which is included, up to 4, also included. Now, is this point a problem? It's not, because it's missing there, but that fills it in. Range. Lowest possible y value in this direction, right? We're squeezing, if we're looking this direction, what's the lowest possible y value? It's going to be -2, which is included. I'm looking at this point here. If this was squished, if all these were squished onto the y-axis, would be the ones that included. So -2 up to 2, but 2 not included. Open circle. There's domain. x-intercepts. Where does it cross the x-axis? Crosses it spots. Here. So those 2 points are 1.5, comma 0, and negative 3.5, comma. Our y-intercepts here, which doesn't look like 0.5, but it's kind of close to 0.5. 0.0, comma 0.6, 0.5 something. Let's keep rolling. C, part C, increasing, decreasing, constant. Where is it increasing? Where are we biking uphill as we bike from left to right? So it's going to be from here, that. We are increasing from, remember, just use parentheses, -4 up to -1. We are decreasing from -1 to 4. And we are constant nowhere. There's no flat 0 slope line that is present. No 0 slope line present. Part D, positive and negative. Positive and a negative. Or is it above the x-axis? There is one region where it's above, and that's this region. All of these x values. So that is from -3. -3.5 up to 1.5. And then where is it negative? There are 2 regions. It falls below in this very small region here, larger region. So let's take a look. It's negative from -4 to -3.5. And then it's also negative from 1.5 up to 4. Sweet. All right, cool. I think we're done with these. We got a good little review going. Let's go ahead and head on and do a fun little exercise where we're going to be detectives. My favorite detective is probably Detective Sean Spencer from Psych. So I'm going to pretend I'm Sean Spencer, and we're going to kind of do things in reverse here. With this example, I'm going to, instead of give you the graph and write the information, I'm giving you the information first, and you can see how this information is enough or almost enough to draw the graph that we need, or at least we can draw something that looks very, very similar. Okay, so I'm going to kind of do these with colors, and we're going to try and piece this together with just from the information that's present. It turns out that, saying the domain is helpful, saying where it's increasing is decreasing is helpful, but first it's nice to kind of plant ourselves on the graph when we're doing one of these on the plane. And I'm going to start actually first by finding the x and y intercepts and putting those. But where does our graph cross these axes? It's kind of like a starting point, almost like when we were graphing with slope-intercept form. I'm going to come over here to -2. We're using our detective strategies. I'm going over to 4, and I'm going to come down to -2 on the y-axis. So I know that my graph has to travel through these points. And I know that it has to go, it's probably going to go like this. So that is super, super helpful. There's also some more information that's helpful. And that has to do with, I'm actually going to use the pink dashed line. I know the domain and range. These are kind of limiting factors for my graph. I know that it's at -5, right? I know that it's at -5 for the low domain, and it goes up to 5, but not quite there, right? So that's going to be maybe an open circle. That could be an open circle there. And then this one will probably be a closed circle because it's included. So we're going to do domain and range with this pink dashed line. It's kind of big. That's okay. Domain. So 1, 2, 3, 4, 5. Okay, I know that my graph doesn't go any lower than that line. And I know that it can't go any higher than this line here. It doesn't go past this line or this line. Now, in the y direction, my graph can't go any lower than right here. Okay, and it can't go any higher than up here. Steady hand, feel like a surgeon, okay? So my function has to be contained kind of within this box to an extent. Like I think it can be on the line is fine. Okay, what's the next one that we know? Oh yeah, this is good. Let's do positive and negative. It says, let's start, it says in this region, right over here, it's positive, so it's above the x-axis when we're from -5 to -2. So over here, we're up in this region. We're in the positive side. So that tells us that what it crosses, it's really coming down kind of like this. So if it's coming down like this, that means it travels through this spot. We don't really know at what angle quite yet. And we know that this one is traveling through on this side because it's positive from 4 to 5. So it crosses back this way. So that's pretty helpful. And it's negative on this side. So we kind of took care of our line in green, so to speak, there. And the last bit of information that's, pretty helpful here is we know that it changes from so it's decreasing at first. We know it's decreasing right here. But where does it change from decreasing to increasing? Well, it starts decreasing and it changes at 1. It changes at 1 from decreasing to increasing. So if I had to guess, so right here is where it changes. I had to guess it's going to come all the way down like this. Now the question is, does it reach that point? Does it reach this point, 1, -3? And we actually know that it does because the range is a bracket there. It comes down to here, and then we're heading up this way. We know it does something like this. Now, do we know how high it goes? Not particularly. We don't. So we can just put an open circle on the line, but we do know it's on that line. And then over here, do we know how high this goes? Well, yeah, we actually do. We know that it goes to all the way to -5, so it's actually on the line. And we know that since this is an open circle, it's got to go. This side has got go all the way up to 6, right? This one has to be an open circle because of where this is headed, or it could be an asymptote, I suppose. But so we're heading up like this, so it's got to go all the way up to here. So we know our function looks. That's pretty cool. I like doing those. Okay, let's keep going. We're going to move on to now, I think is a pretty simple calculation about talking about how things change, but we've kind of did that in Algebra 1. This is just a new way to look at it in kind of more of a physical problem setting. Okay, and the graph below displays the distance s of t that a car has driven as a function of the number of hours, t. What is the average speed over the 3-hour time interval indicated in this graph? How would you find the average rate of change more generally? This formula familiar. So we have an area of time that's kind of presented in this graph, right? And so you want to look at the average rate of change here. Gave a little bit away there. Oops. Okay, if you want to talk about how things are changing, you look at the big picture, right? We'd say, how is this car changing? How is its distance, the distance that it's driven, how is that changing? And it turns out that the car has driven 150 miles over that 3-hour period. So we can say if it's driven 150 miles in 3 hours, we know that as a whole, on average throughout that time period, it's driven 150 divided by 3 is 50 miles every 1 hour, right? If we simplify this fraction. And 50 miles or 50 mph. So we know that it's driven 50 mph. And if we take a look at this thing, we look at this and we go, all right, well, that's pretty obvious. We can kind of take a look at this. We can actually line. You draw a line from this point to this point. You can see a car that drives 50 miles an hour the whole time will get to the exact same distance in the same amount of time as this vehicle. So that's kind of why we say it's the average rate of change in this instance. Is the car that follows the red line, is it driving the same speed the whole time? Well, in the first hour, it really doesn't go very far. But if you look at the distance that it travels in the last hour, it really, really picks up its pace. So this car started going much, much faster in the last hour than it did in the first. Maybe it was climbing a hill here, leveled out on flat here, and maybe it was going down a hill during this hour. Yeah, so how could we find kind of the rate of change more generally? Well, if we can draw a line to find that average rate of change, it's really just a slope. So to find the average rate of change between kind of 2 points in time or 2 points on a graph, all we have to do is find those two endpoints, figure out where they would be or estimate them from the graph, and then use the slope equation, and that will get us to the right spot. Let's take a look at this example here. The graph below shows the depth of water W in a reservoir over a 1 year period as a function of the number of days, X, since the beginning of the year. Using the graph, describe how the amount of water in the reservoir changes over time. Then find the average rate of change between W of X equals 100 and 150, then between 150 and 200. Okay. Let's think about what's happening here. So the reservoir, the amount of water goes up. So maybe it starts kind of a wet period here. It's starting to rain a lot in the region. And then it doesn't rain for what appears to be like 150 days. So the water in the reservoir drains down, 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 down. It's being used by, farmers or whatnot. And then maybe the rain picks back up from here to here. So if we want to find the average rate of change between X equals 100 right here and X equals 150 right here, we want to look at these 2 points in time, like so. Looking at these 2 points in time. So this point is the point we can kind of estimate. It looks like 100, comma, it's pretty darn close to 70. I'll say 100. This one looks to me 150, comma, and I'll guess halfway-ish, maybe a little bit lower. I'll say looks like at 150 we're up here at 80. To find the average rate of change, all that we are really doing finding this between those points. We're saying, all right, well, let's calculate that slope. Let's do y minus y1 over x2, x1. Okay? So we can do that. We can say y minus y1. Let's do 85 minus 75 divided by 150, 100. We end up with here 10 over 50. Which if we did double the top, double the bottom, that would be 0.2. And that will be change in y over change in x. Units of y, in this case, or W, okay, are feet, 0.2 feet per day. So what's happening over this period, right? We ended up getting a positive slope. Over this period of time from the 100-day mark to the 150-day mark, on average, every day we're gaining around, a couple inches of water in the reservoir, which is pretty exciting. Hooray. Okay, that was the first change or the first kind of time period we were looking at. The next one is between 150, which we already know, and then this data point right here, which is pretty obviously 200, 50. Okay, so this is a different line. This one, we're at this stage in our water journey, we're losing water here, so we should hopefully end up with a negative slope when we do our math. So to calculate the rate of change on average between those 2 points, we can do, see here, that'll be 50 minus 85, y2 minus y1 over 200 minus 150. 50 minus 85, is that 35? Negative 35. All right, double the top, double the bottom. End up here with negative 70 over 100, which is really negative 0.7 feet per day. What does this mean? It means in this, from 150 days to 200 days, on average, they were losing around 1 foot of water per day out of the reservoir. So it was being eliminated or being cleared out from the reservoir much faster than the previous 50 days were able to put water into the reservoir. Yeah, and so this kind of collects a little bit of information, and I think it's true that since this is a 50-day period and this is a 50-day period, they're the same length. Only because they're the same length, we can actually average these two numbers and then get the resulting slope between these 2 points here. It doesn't ask us to do that, but I find that pretty interesting. So we could say, like, what's 0.2 plus 0.7? Add those together, you get negative 0.5. And then you would divide by 2, which is negative 0.25, which I would be willing to bet is the slope between these 2 points. Okay. Cool. All right, now our last example here, our last 3 examples are, we're doing the same thing, but I'm taking the graph away from you. And so we're saying, like, can we look at a function and can we talk about the rates of change over those intervals? And we're going to do kind of the same thing we were doing before, right? We're going to look at the rate of change at an interval, and we're going to see how things or how they compare when we look at it in sections versus the whole length. So let's start by kind of graphing this. What does f of x equals 2 look like? F of x equals 2 or y equals 2. Okay, f of x equals 2 is just a horizontal line. It's all the points with the y value equal to 2. Okay, that collection of points, all the points with the y value equal to 2. All right, let's take a look at the average rate of change between a couple points in here. So let's look from -1 to 0. Let's look from 0 to 2, and then let's look from -1 to 2. So if we look at the values, it's kind of a silly thing for us to do. Because when we look at the average rate of change from this section, what's the rate of change here? Well, if you can't really do any math because the slope is 0. What's the value, the rate of change from here to here? It's flat. The slope is 0. So when you look at the rate of change here, it's 0. When you look at the rate of change here, it's 0. And when you look at the rate of change for the whole interval, that's going to be 0 as well. It's just a flat line. So we just say the average rate of change, it's not changing. It's constant. It's not, it's constant. It's not changing. So in this case, it's 0, and there's nothing really super interesting to say here other than when we have a line, or when our function is linear, there will be a constant rate of change. So let's write that down. So when function is linear, there is a constant rate of change. So if a problem asks you, hey, can you find the average rate of change for this thing? And then it gives you like a line. Why did I add a question mark? There is a constant rate? Okay, when it gives you a line, there's no sense in doing all the calculations, and it's not worth your time, because there's a constant rate of change, and that change is m. It's going to be the same over every possible interval that you could construct. Okay, let's take a look at this one. Perfect example. This says f of x equals 2x, or y equals 2x minus 5. You should have a little light bulb going off there. Ding, 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 ding. Okay, got to get that filament. Okay, because this is in slope-intercept form. If it says, please find the rate of change from, suppose, 1 minus 5. Okay, when you look at this, I got a positive slope of 2. You go up 2 over 1, up 2 over 1. Not my finest work. When you're looking at these points on the line, and you want to calculate the rate of change, well, here, between -1 and 0, right, we can kind of draw a line here. Between -1 and 0, you rise 2, you run 1. It's got the slope of 2. Okay, let's look at another interval. When you look from 0 up to 2, okay, when you look from 0 to 2, we run 2 and we rise a total of, it's not quite on the line, we rise a total of 4, up 2 over 1. That's a little bit funky. Okay, so we rise 2, run 4. This region, rise over run, is still 4 divided by 2 is still 2. And when you, just so you're convinced, when you go from this point down here all the way up to this point, you have risen a total of 4, 5, 6, and run a total of 3. 6 divided by 3, it's still 2. In this case, since this is a line, the constant rate, or the rate of change over every interval is always the slope, is just 2. Now let's do like a good one. I'm going to be maybe a little more accurate with my drawing here. Got a line there, and we'll do a horizontal line down here. Throw a couple tick marks on there. Let's blow this thing up here. 1, 2, 4, 5. Got our y-axis, we got our x-axis. This is some of you guys may recognize this. This is actually a parabola. And to show you the points that we're going to get on this, I'm going to make a little t-table. So I'll draw my x and my y. And we're just going to plug in some numbers that are easy to do math with. And really, those numbers are going to involve the intervals that we already have, right? The lowest value we have is -1. Go to -1, 0. I'll plug in 1. And 2 as well. And so I'm just going to do these verbally. I'm not going to write them out. But if you plug in -1 in for x, what's this, y, or f of x, I should say. -1 squared is 1. 1 plus 1 is 2. Plug in 0. 0 squared is 0. 0 plus 1 is 1. 1 squared is 1. 1 plus 1 is 2. 2 squared is 4. 4 plus 1 is 5. Now we're going to plot these points. And if you don't mind, I'll just keep using red. All right, 0, 1. So negative 1, 2. 1, 2. And 2, 1, 2, 3, 5. All right, this is a parabola. This is something that is curved. Actually kind of travels like this if we were to plug in a bunch of other points. And we have not graphed everything here. This continues up and this continues up. But it's asking us to find the average rate of change. So if I ask you to do that for a function, actually not too bad. So the first one, we're going to find the average rate of change from -1 to 0. How do we do that? Well, we just calculate the slope. And you can do that with, pretty quickly with the points that are given, right? We have the values that are given here. So basically we can say from -1 to 0, what's our slope? Well, we can do y2 minus y1 over x2 minus x1 if you want, or you can just kind of count what's going on here. So you can say, all right, it looks like for this little line, I went down 1, right? Down 1. I know my slope is negative here. My rise was 1. My run was 1. So that gives us a slope of -1. Okay, and then the next one, the next region from blue, 0 to 2. So the average rate of change is going to be whatever the slope of this line is. That's from 0 to 2. And so when we're doing that, really similar, count the rise. We know this is positive slope. I go up 4 and over 2. So I went up 4 and over 2, which gives us a slope of 2. Up 4 over 2. Okay, and lastly, -1 up to 2. Okay, from -1 up to 2, we calculate the change. Now notice, we started a little higher, we came down, so this slope is not quite as much. How much did we go? Well, this is also positive slope. Our rise in this case, we went up 1, 2, 3. And our run was 1, 2, 3. This has a slope of 1. So the average rate of change over each of these intervals is different. Now, you'll notice that when I average these two, you won't get this value, but that's because the blue interval is wider than the green interval. So you'd have to do a weighted average in order to get the correct value there, but that's maybe a little bit beyond what we've done for that. Okay. All right, guys, thanks for tuning into the video today. I hope you enjoyed it. And yeah, we'll see you next time.